So, hi everyone, I'm Mirgita Frasheri, I'm a postdoc here at AU, and today I will tell you a bit about the RabbitMQ FMU and its role in bridging the co-simulation world with the outside or external world. So let's jump jump right into it. So here on the left and green side, we have our co-simulation world and the different parts of it that have been covered by my colleagues previously. So here we can imagine that we have in the co-simulation different FMUs that are realized for different purposes and simulating different parts of the system. And then we have what is the world that is outside this, the INTO-CPS application. And here by the real world, of course, we can mean like a robot. And here it's pictured the Robotic, the field robot by Agro, which you will hear a bit more about a bit later in this presentation. But also this could be a gazebo simulation. So instead of having the actual robot, we can have the model of the Robotic and then we are running it in gazebo. So here then the question is, how do we get this, meaningful communication between these two worlds? So how do we actually bridge them together? And of course, this kind of the answer to this question is hinted in the title. So basically here the key role is from the RabbitMQ FMU, which will exactly realize this connection. So, but why is it useful, right? Because so far you might be saying, okay, this sounds like a nice idea, but then why do we care for it? Why do we want it? So the first answer to that is that we are able to simulate with other components that cannot be so maybe easily packaged as FMUs and put inside the context of the INTO-CPS application, like for instance, the gazebo simulation. And by having this functionality, then we are able to couple the different systems together and run our tests. And then the second reason is also something that Peter also mentioned in the beginning of today's webinar, is that this is useful in the realization of the digital twin concept. So we might be having our modeling our digital twin inside the INTO-CPS application. We may be having also different monitors that are tracking the different aspects of the behavior of the robot. And we are, of course, interested in getting like live data from what the robot is doing, or just maybe thinking of the position of the robot. And we also want to be able to reason on this data and kind of send commands if it's necessary, like it would be in the case of a monitor tracking the behavior. So regarding RabbitMQ development, in the current release, what is possible to do is that one line of the communication that is from the outside world through the RabbitMQ server, the RabbitMQ FMU, and inside the INTO-CPS application. And this can be configured very easily by looking into the model description file and adding there the different outputs as are needed, basically, and then they can be connected to other FMUs as needed. So for the upcoming release, and this is where I joined the team, then we have two things that we needed to address. So the first thing had to do with closing the loop on the communication. And the second thing had to do in a bit addressing that meaningful communication that I mentioned earlier. So let's take them one at a time. So in order to close the loop on communication, what we said is that, okay, we need to allow the user to specify as many inputs as she wants, and this can be done as usual in the model description file. And then what we do is that if there is a change between the inputs, between two consecutive time steps, then we package these inputs and send them off to the Rabbit and to whoever is listening on the outside. So this means that only the inputs that have changed will be sent, and this alleviates the burden on the other side to kind of figure out what is new, what has changed, and what has not changed. So this is one aspect. And the second aspect now, which is a bit also quite important, it has to do with what happens if our co-simulation and what we have here on the other side, the real world, they are maybe not they are not synchronized in time in the sense that one can be ahead or behind of the other. So when it comes to the co-simulation being ahead in time, this is something that we can up to some point control, because through a parameter for the RabbitMQ FMU that has to do with the age of the data. So the RabbitMQ FMU, it will step during or continue to the next step when it has valid data. And then what is valid then can be decided on the age of this data. So by this, playing with this parameter, we can kind of allow the co-simulation to go ahead a little bit if it's of course performing faster than what is on the other side. However, the other problem is a bit trickier to control, or we cannot really control it directly, and it has to do that, okay, what if my system, my robot or my gazebo simulation, maybe it's sending too much data, or maybe it's sending big messages, so then these will take a long time to process. So then what is going on the co-simulation side is that the system is getting behind. So now if we go back to this idea of having a monitor that is kind of doing some calculations on this data and sending some feedback to the robot, of course we can see the problem there if our co-simulation is too far behind, that the messages that we are then sending to the robot don't really make more sense. So here then the idea is to kind of be able to tell when this happens. So be able to tell if the co-simulation is falling behind or is getting ahead in time, and then inform the user of what is going on, such that we not only have two systems that are running together and sharing data, but this is also, it can give us an idea of the time discrepancy that there is between them. So the state of this upcoming release, so we are planning to have this out in the upcoming days. So we are doing now the final touches and to the code, and hopefully this will come out quite soon. So the RabbitMQ FMU, of course, it's quite general in purpose, so it's not really tied to anything. But then, of course, for us, it's quite relevant in the Agro Robotic Fleet project that is in collaboration with Agro Intelli. And so the scenario is a bit like this. We have these different robots, which are the Arabo robots developed and produced by Agro Intelli, which are supposed to autonomously do different operations in the field, like seeding operations. We can have here in this field also farmers, and there is no really restrictions in terms of, like, we cannot really assume that there cannot be humans or unexpected people that kind of pop up out of the suddenly. So then the idea is that what we want is to be able from the cloud to send a plan to these robots in terms of what they should be doing and what kind of paths they should be following. But also have this communication in between the robots themselves, because there might be data that might be shared between these robots if like there is an unexpected event happening, like a human or a kid, for instance, pops up out of nowhere. This can be something that can be shared between these robots. So all of this, and the key here is, since we also we don't really assume a scenario in which we don't have like people at all that might pop up, is to have all of this in a safe manner. So actually safety is quite a key aspect in this project. And what this means for the work that we have to do, so it's again on two levels. So on one side, we want to be able to simulate different scenarios and be able to see if different safety constraints that we are putting are being satisfied. Like, for instance, one safety constraint could be, of course, keeping a safety distance to humans or to obstacles. And we would like to be able to test different scenarios. And these different scenarios, you can think in terms of, we want to simulate scenarios, for instance, where the network is degraded at different degrees with different delays. We might want to simulate scenarios with different obstacles or other events, like, for instance, some part of the robot is suddenly not working as expected, and we still want to see in the end that it will behave in a safe way, so it will stop in most cases and not injure or harm first the people, but of course also other equipment or the field itself. So here then the role of the RabbitMQ is more in terms of going back to the first reason as to why it's useful, is that exactly it allows us to combine in simulation like what we can have on the INTO-CPS side with the different FMUs and other systems, like, for instance, a robotic model simulated on Gazebo. So we are able to RabbitMQ then to start up, we can be able in principle to start up the system by setting up the different parameters that will reach the other side through the RabbitMQ. And then the other part, which this is also quite strongly connected to safety, and it has to do with the realization of the safety monitor through the digital twin concept. And here again, the RabbitMQ is an enabling FMU that allows us to now we remove our gazebo simulation and we plug in our actual robotic. And immediately we can have like this flow of data that is coming from the robot inside the INTO-CPS application, and we can have our monitors that are tracking different aspects of the behavior of the robot and sending feedback, intervening when this is necessary. So now, of course, if we use this the example of the safety distance, you might be very well thinking, but the robot should probably have some kind of check itself, right? We don't really want to rely on something that might be far away from it to tell it to stop, and this, of course, is true. But this is more a proof of concept in terms of how we can close the loop in a meaningful way. So, of course, by having the RabbitMQ FMU, then we can now focus on actually what is going to go into this monitoring side. So this would look a bit something like this. So now the thing is that it's not really to make smaller tests with, and this is why we have a smaller version of it, which is the desktop robotic, and which some of our bachelor students are now working with. And now, so I will show you a small video, and this is very raw in a sense that we don't really, for instance, have an actual obstacle yet. So the position of the obstacle is given. So the robot is not really checking for anything, as there is nothing there. But the main idea is to show the connection. So let's see if this works. So here what they are doing is just showing the different components that they need to run. So this would be RVs, where they have collect the data, and then the different ROS nodes that are needed to communicate with the desktop robotic. And then here we have the INTO-CPS side. And then we can see our, maybe a bit better, our desktop robotic, which is actually quite practical to do our tests with. And here it will basically start moving, and then it will stop immediately. And this stop is a command that it received from the safety monitor, because the safety monitor that is running on the INTO-CPS side has actually realized that the distance is below what is allowed. So then it sends this stop mechanism. So more nicer way we can see here, and this would be something that it's possible to inspect on the INTO-CPS application side, where you can plot the different the values of the different variables. So here what is interesting for us is this orange line here, which is basically the distance between our desktop robotic and this fictitious obstacle. And then we can see here how the distance is getting smaller as the robot is moving forward. Then we have the red and the purple lines, which are the expose, and this is of course the only thing we need, since the robot is moving only along one axis. And here with the green line, we can actually see the exact moment where the safety monitor said, you have to stop now because you have trespassed this safety distance that has been set. So regarding the future development, one big thing that we are kind of still discussing with the guys, it has to do with the mitigation strategies for this to kind of counteract this time discrepancy. And the bigger question here is it whether what role should the RabbitMQ have in all this, in the sense that so far the RabbitMQ will only notify you about this time discrepancy, and it will not really do anything about it. So then the question, as I said, is should it actually do anything, or should it have more of an enabling role, such that it can be reconfigured somehow to kind of by some external manager entity that can make a plan about when such time discrepancy takes place. So this is still an ongoing discussion. We don't really want to give too much decision-making power to the RabbitMQ, as we feel its purpose, and this is something more reserved to another level of reasoning. And with this, I will conclude my presentation, and if you have any questions, I will do my best to answer.